Up to now, the combinational circuits that we've looked at have been fairly arbitrary. We've invented truth table output columns out of nowhere or for peculiar functions just so that we can have something from which to create a circuit or write a Boolean expression. Well, in this video, we're going to look at some common combinational functions that are combinational circuits that are in computers, particularly those that compare numbers to see whether or not they're different, those that shift numbers, and those that rotate them. So to begin with, we'll look at comparing numbers. So the idea here is we'll have two numbers at any given time, and they're arbitrary bit patterns. In this example, I'm just using two 5-bit numbers. Now they're similar, but they're not the same, and what we need is a circuit that can determine whether or not they're different. Presumably, if our focus is to determine that they're different, we're going to be looking for producing a 1 as output of this circuit if the two numbers, which have multiple bits each as input, are different at all, or we'll put out a 0 if they are the same, indicating 0 that they are not different. You could almost imagine different with a inversion bar over it. So over here, I've got a 2-input column truth table with a sub I and b sub I as inputs, indicating the ith bit, some arbitrary I of A, and the same bit position from B. And what we're going to do is for each bit position, we're going to see whether or not that position is the same, because in the end, if any bit pair differs, then the numbers are different. So if we make this truth table together, or the input columns, we can then see that, well, 0 and 0 are the same, so they're not different. 0 and 1 are different, so we say 1, different. 1 and 0 are different, and 1 and 1 are not different. And very quickly we notice that this is the same output for a 2-input exclusive OR. So that means to compare each of our individual bits, we just need an exclusive OR. So I've bussed down all 3 bits in a 3-bit comparison circuit, all 3 bits of some arbitrary value A, and all 3 bits of an arbitrary number B. And then what you can see here is I've got 3 exclusive ORs, 1 for each of the positions in these 3-bit numbers. So this is the exclusive OR that handles the 0th bits. And what we can see is B sub 0 runs into it and A sub 0 runs into it. The next gets B sub 1 and A sub 1, and the last gets B sub 2 and A sub 2. Now up here we said if any bit pair differs, then the numbers are different. So if this one produces a 1, we want the greater output of this circuit to produce a 1. Or if this one produces a 1, we want the greater output to be a 1. Or if this one produces a 1, the greater output should produce a 1. So to connect these 3 individual circuits that compare the bit pairs, all we need is an OR. Because that's literally what we were just saying to describe how this works. So it's not too complicated. So there we go, we have a nice comparison circuit. Now let's look at circuits that shift and rotate numbers. And lined up in there. All right, we'll start with a quick recap on what shifting and rotating means. So with shifting, we can either go to the left or to the right, and SHL is sort of a well-recognized abbreviation for shifting to the left, SHR, same for the right. So I've given each of these as functions with the input bit patterns 0, 1, 1, 0, 1. So if we shift that to the left, what's going to happen is, and we're going to treat this as a single bit shift. The leftmost position is going to fall off, that 0 falls off into the bit bucket, so it's lost forever, and all the other bits slide over 1 position so that this 1 in the original number, second from highest bit, becomes the new highest bit in the result. And each individual bit just comes over 1 to the left. Now that leaves a vacuum at the end. And what we do always when we're shifting to the left is we fill the shift vacuums with 0. So a new 0 comes in. But it's only a coincidence that there was a 0 in the high order bit before. So this is a vacuum filling 0 and nothing more. If we were to shift the same bit pattern to the right, then all of these 4 bits up high will move over 1 to the right. But the lowest order bit, the 1, it's going to sort of disappear into the bit bucket and be lost. And then again, we have a vacuum that needs to be filled. Now, for the sake of simplicity in this lecture, we're just going to say that this one is unsigned, and so we always are going to arbitrarily fill in with a 0. And when we get to making the circuit for this, we'll make sure that we include sign extension. But if this were a signed value and you shift to the right, you always make duplicates in the vacuum space of the original bit that was the sign bit before the operation occurred. So if this number here had a 1 in the high order bit in the sign bit location, as we shifted over to the right, we would have introduced a 1 into the vacuum, not a 0. Rotating is utterly similar to shifting. The only difference is the bits that we've seen going off into the bit bucket don't go to the bit bucket. They wrap around to the other side because the entire bit pattern does a single bit rotate. So here, when we rotate to the left, this 0 is going to fall away off the left edge and then fill in the vacuum created. This other bit pattern, it has a 1 in the high order bit, and when that 1 is shifted to, or rotated to the left, it falls off the end and comes and fills in the vacuum with itself. So this vacuum on the right when you're doing rotates, is going to be filled in with whatever the bit is on the other side. And the same thing is true if we rotate to the right. So when I rotate this bit pattern to the right, this 1 at the end falls off, but then comes back around to fill the vacuum on the left. Over here, the 0 at the end falls off and comes all the way back around to the left to fill in the vacuum left when this 1 shifts over to the right. Okay, so we just need to make a circuit that can perform these functions. And because they're so related, these are typically implemented in a single circuit. And so that circuit is going to perform a number of functions. It's going to perform shifting, where the bits just go to the right or to the left. It's going to perform rotations, where they go to the right or the left, but the ends wrap around, depending on your direction. But also, we want to make this circuit complete. And so when we're doing shifting, particularly shifting to the right, we want to pay attention to that highest order bit up here, right? We want to make that highest order bit sign extend as things shift over. So we need to make one circuit that does all of that. Let's start with a real simple model for one. So we're going to make a 3-bit shifter rotator circuit. And I've gone ahead and created a bus for our 3 bits of original input, which is a 3-bit number, but we'll call D. But then we're going to have a variety of additional control lines that are bussed down to be used by all of these different circuits over here. We're going to have a left wire or left pin indicating whether or not we are going to the left or going to the right in our shift or rotate operation. So since it's called left, this means that a 1 on this wire indicates we're going left. A 0 on this wire indicates we're going right. Another control pin is the shift pin. If there's a 1 on the shift pin, we are shifting. If there's a 0 on the shift pin, then we're rotating. The sign bit indicates whether or not this is a signed operation, which really only matters under the circumstance that we're doing a right shift. So the signed pin, you'll see, is not really utilized ever, except under the circumstance that we are doing a shift to the right. So that one's not going to be highly used, but it's important if we want to make sure our circuit also supports sign extension. Otherwise, we're just throwing zeros into the holes whenever we shift, and it's not usable for shift as a form of fast mathematics. All right, so let's start with this middle piece of output. Let me talk about the output layer here. You'll notice what appears to be a small multiplexer here, a layer of AND gates going into an OR gate, a layer of AND gates going into an OR gate. Another layer, this one has 3 AND gates, and we'll have to get to why that is later, going into an OR gate. But this is because effectively this shifting, rotating circuit with possible sign extension is really just 3 individual circuits where we're sending in 3 bits of data along with some control information, and we're getting 3 new bits that represent a 3-bit number. So this is the high order bit, the middle bit, and the low order bit. And what we're going to do here can be scaled to an arbitrary number of bits trivially, because this one here in the middle is basically not affected in any fun way by whether or not we're shifting or rotating, and whether or not this is a signed or unsigned operation. This bit here in the middle, and any multiple bits that were in the middle, like in the case that we do a 5-bit one, the 3 that are in the middle, they basically just acquire whatever is next to them based on the direction, so they're easy to work with. So let's solve that part right away. So x sub 1 is really the middle bit, and it's going to matter to us whether we're going to the left or to the right. So let's start with going to the left, just for the sake of it. So if we're going to the left, that means the left pin has a 1 on it, and so this AND gate is going to have an input that looks like a 1, because it doesn't have an inversion bubble. And we're going to drag it over here and connect it to the left pin bus. So this AND gate, remember that the AND gates can work like transistors and allow the gating of data to go through. These control lines are going to effectively allow individual AND gates to accept one of these data inputs and pass it on out the multiplexer. That's how this is going to work. So when we are shifting to the left, we think about this up here, shifting to the left, the middle value is going to get its bit from the thing to the right of it. So in the case of our output x sub 1, it really is just going to become d sub 0. So we connect the left pin to it, and then we connect our data pin, which in the past I have used blue for, so I will use it now to make it clear that it's data. We'll connect this right to d sub 0. So whenever the left pin is high, d sub 0 is going to come out of this middle pin. All right, let's do the other circumstance for that middle bit. The middle bit could get whatever is in D2 if we're shifting to the right. So to shift to the right, we need to invert our left signal, because if left has a 1 on it, that's going to turn into a 0 and disable this AND bit from pumping out anything other than zeros. But if it's a 0, which means we intend to go to the right, that 0 will come down, get inverted to a 1, and now we're gating this AND so that we're letting the data line that will connect to this go on through to the OR gate. So in this case, that data line is coming from D sub 2. All right, so we're looking pretty good. Now this one down here has 3 AND gates, so it's clearly more complicated than this other one that only has 2. So we'll go to the low order bit of our output next. So in this case, when we're all the way at the end, this is x sub 0 is like the position d sub 0 is in. It matters to us whether we're shifting or rotating, particularly if we're going to the left. So over here, if we shift to the left, then d sub 0 will be routed into d sub 1. That's what we got here. However, d sub 0 needs to have something in it. And whenever we're going to the left, if it's a shift, then d sub 0 needs to end up with a 0 in it. Now, the nice thing about a multiplexer is, unless these AND gates fire off some piece of data, right, and putting 0 into this position isn't really like feeding one of these data bits. It's sort of something else, just running ground to it or something. We don't actually need to map the condition for doing a left shift and making sure a 0 comes out. If we don't map left shifting to either of these two AND gates, then whenever the control pins say do a left shift, neither AND gate will fire, which will route a 0 out of each, and 0 or 0 will be 0. So it'll already cover our condition for us. We only need to care about these AND gates when we're actually routing real data from the original number. And so shifting is of no consequence to us here when we're going to the left, right? So let's look at what does matter when we're going to the left. Well, it's a rotate. So if I rotate to the left, D0 moves into D1. The original D1 goes into D2, and D2 needs to come around. So on a left rotate, we want to put D2 here. So let's identify that it's a left rotate. First, it's not a shift. Second, it's a left action. So that indicates left, not shift or rotate. And then the data line that connects to this is going to be D2 because it wraps around. There's D2. Beautiful. Not really right on the connection though. Okay, there we go. Now what about this bottom one? Well, in the bottom one, since we've already covered the concept for both types of left thing. Left shifting, we're just not going to cover because it'll produce a 0. Left rotating, we get from D2. So what about when we go to the right? Well, does it matter whether it's a shift or a rotate, or if it's signed or unsigned? It doesn't. If we're going to the right, D0 is just going to get whatever is in D1. So the main thing we do here is say that we're not going left. When we're not going left, we must be going to the right. So grab D1 and put it in D0, or X sub 0, the output in the low order bit position. And there we go. So this top part is done. 2 simple conditions. All other conditions produce 0 as output. All right, now in the high order bit of our output, we only have one more AND gate because we have more conditions really that matter. When we are shifting to the right, we're going to have to worry about whether it's signed or unsigned. So at least 2 of these, well, one of them is going to have to deal with it being signed. Because when it's signed, we're going to take the original sign bit and duplicate it back into itself as it's also shifted over. Right? So one of these conditions is going to be sign extension. And I think I want to put that one down here at the bottom. And keeping in line with these, we'll do left at the top and then move to the right. But then there's also, if we're going to be doing some operation where we're moving to the left. Well, if we're moving to the left and we're in the high order bit, it doesn't matter whether it's a rotate or a shift. D1 is just going to come into D2. So we can make that happen here. The other condition that we have to concern ourselves with is when we're going to the right, but it's not a shift, it's a rotate. If we're going to the right and it's a rotate, then D2, or X sub 2, I should say, that last position, the high order position, is going to come from the original low order position. But what about if it is a right shift and it's unsigned? Well, just like we did up here, if it is, then we just need to produce a 0 out here. So we'll get a 0 here if it's not any of these 3 conditions in the first place. So we only need to worry about doing left anything, or doing a right rotation, or a signed right shift. And if it's not one of those, well, it must be the only thing left, in which case we get a 0 here. So everything should work out nice and smooth. So if we're doing left anything, let's make that connection to left. If we're doing left anything, then D1 is going to move into this high order position. Oh no, that was supposed to be a blue wire! The world will forever see this video and laugh. Oh well. For the middle one, so now we have, if you do left shift or left rotate, whether it's signed or unsigned. Notice still, we haven't used that signed wire for anything. All right, in this condition, what we'll do is handle a right rotate. So if it's a right rotate, first of all, it's not a shift. So we'll say it's not a shift. And if it's to the right, well, it's not left. So we'll mark that it's not left. And then this time, to make up for our black blunder here, we will use the blue as we had everywhere else. And we'll connect this, again, since we're doing a right rotate, that means D0 will wrap around into this high order bit position. And there it is. All right, for our final piece of output, or our final condition that we need to route data for, is when we have a signed right shift. When we're doing a signed right shift, we need to sign extend. So first of all, we'll mark that it's signed by connecting a straight wire there. We'll identify that it's a shift, but it needs to be to the right, so it's not left. Okay. And in that circumstance, when we're doing a signed right shift, D2 will move into the bit position of its right, but it'll be duplicated where it already was. We're going to route D2 to this final AND gate. So take this over in blue, and there we have it. So we've got three pretty interesting circuits. One for comparing numbers to determine if they are different. If you want to compare numbers to determine that they are the same, and you want it to produce a 1 when they're the same, you just take the circuit we already made and invert the output. Put an inverter on the end of that OR gate, and you've got yourself a comparison circuit that tells you 1 if the circuits are the same. We've also looked at shifting and rotating and considered unsigned versus signed shifting. And we made a single circuit that is a left-right shifter, rotator, unsigned signeder. And that's great because it performs all of those functions. If you've got any questions, please leave them in the comments below. And hopefully we'll get you some more great videos on how computer circuits work.